Good morning, everybody. This is Mukherjee, working as Associate Professor in Physics of SNS Department, St. Peter's Indian College, Hyderabad. Today, our topic of discussion is quantum mechanics. And this quantum mechanics is the syllabus of applied physics corresponds to Unit 1. So let us discuss about quantum mechanics. Now, before going to quantum mechanics, we need to know what are the mechanics. Mechanics, study of matter. The study of matter we call it as mechanics. And this mechanics is basically classified into classical and quantum. Before that, let us go back to this universe. How do we define this universe? The universe is very simple. If we want to define universe in a very simple terms, how can we define? Universe is basically classified into two things. One is matter and the other one is energy. So if I want to define universe in a very simple way, the universe can be defined as matter and energy. Now once again matter. Matter is further classified into, we have three kinds. What are they? Solids, liquids and gases. Anyway, energy we have basically two things. What are they? First one is the kinetic energy and the second one is potential energy. Anyway, this matter can be converted to energy, energy can be converted into matter, and that is what energy conservation principle is. So energy conservation principle says that energy can neither be created nor destroyed, but it can be converted. So matter is converted into energy or energy is converted into matter. So how do we define the universe? The universe is simply made up of matter and energy. Matter is classified into solids, liquids and gases. Energy is classified into kinetic energy and potential energy. Now these liquids and gases, both of them, they correspond to fluids. So we have solids and fluids. Now there is a difference between the solids and fluids. The solids, they have some definite properties because it's solid. Fluid, they don't have a definite property. That doesn't mean that they don't have properties. They have properties, but the properties are not so definite compared to the solids we have. Therefore, our point of interest will be the solids. So, universe to matter to energy, then matter to solids, liquids and gases to fluids, and then solids. Now, how do we classify these solids? Once again, these solids are classified into two categories. What are they? The first one is amorphous. And the second one is crystalline. So these solids are classified into two categories. What are they? The first one is amorphous and the second one is crystalline. And what is the difference between these two, amorphous and crystalline? It's very simple. If we take a crystalline, the crystalline solid, let us assume that this is a crystalline solid. Of this crystalline solid, if I want to remove a very small piece of it, this piece contains all the properties what this piece contains. If I want to remove a small sample from this, let us assume that this is a small sample. This small sample consists of all the properties what this bigger sample contains. This is what we call it as crystalline. But amorphous, on the contrary, doesn't have these properties. And therefore, our point of interest is now to crystalline. Why? Because it has some definite properties and regular. Might not be uniform, but they are definite and they are regular. So we want to understand this crystalline properties. So universe is classified into matter and energy, energy to kinetic energy, potential energy. Once again, matter to solids, liquids and gases, and then solids are classified amorphous and crystalline. So we are able to identify or we are able to understand what exactly is this crystalline is. But how these crystalline amorphous are formed, how these solids and liquids are formed, how this matter and energy is formed, we don't have any definite answers for these questions. And therefore, some scientists, some physicists, they try to answer this behavioral distribution of this matter and energy. Of that, the first one corresponds to the classical healing. Of course, this classical healing is something related to both energy as well as matter. So we want to understand what is this classical healing. So the classical healing, we call it as classical mechanics. So we have this classical mechanics. So what is this classical mechanics? The mechanics or the theory which is being called as classical theory, which exactly gave us the understanding of how the matter is distributed, how the energy is distributed, and what are the properties of life. So all these properties which have been defined or designed with respect to classical theory, we call it as classical mechanics, or this theory is before quantum theory. When Planck's quantum theory comes into picture, this theory was existing before quantum theory or quantum theory by Planck. So we call it as classical mechanics. And according to classical mechanics, the fundamental thing is, it says that energy is continuous. This is the first thing. Energy is continuous. And the energy is always proportional to wavelength. Or in fact, energy is a function of wavelength. So what is this we have? Energy is continuous, and what is the other we have? Energy is a function of wavelength. And we call them as the particles. These particles are consisting of molecules, and these molecules are giving a definite shape to the solids and indefinite shape to the liquids or fluids and gases. So these are some fundamental properties of the classical mechanics. But we have one thing called as ultraviolet catastrophe. We have this called as ultraviolet catastrophe. And this ultraviolet catastrophe is not exactly satisfying the theory given by classical mechanics. So let us see what exactly is this ultraviolet catastrophe is. Let us see what exactly is this ultraviolet catastrophe. Let us say this is the energy distribution. So this is the energy distribution, and this is the temperature. This is a constant temperature, like you have 300 Kelvin, then you have 1500 Kelvin, 1750 Kelvin, and 2000 Kelvin. So at fixed temperature, the variation of intensity with respect to energy is represented in the graph. So now what is happening? As we are increasing the energy, the intensity is getting increased. After some particular point, what is happening? It is getting decreased at 300 Kelvin, which is fixed. And the second one is at 1500 Kelvin, which is fixed. And 1750 Kelvin is fixed. And 2000 Kelvin it is fixed. But the problem is, this 300 Kelvin, 1500 Kelvin, 1750 Kelvin and 2000 Kelvin, it is distributed, it is moving towards the left side. This peak is exactly moving towards the left side. But actually, according to classical theory, what it says, as the intensity increases or as the energy increases, the intensity should also increase continuously. So energy increases, the intensity should also increase continuously, and this continue should happen implies that these peaks should move towards the right side. But in reality, what is happening? They are moving towards the left side. The peak is moving towards the left side. And this could not be explained properly by classical theory. And this classical theory was exactly supported by Weymouth's law and Rayleigh-Jean's law. Anyway, they are out of the syllabus, scope of the syllabus, but still, there was no proper theory to explain this behavioral property of energy versus intensity. And therefore, classical mechanics has a big failure in explaining this. That's why we call it as ultraviolet catastrophe. And therefore, to solve this problem or to explain this abnormality, quantum mechanics comes into the picture. So let us see what is this quantum mechanics is. Let us try to understand what exactly is this quantum mechanics. Now, what is quantum mechanics? It's very simple. Quantum, which has been a word which has been derived from quanta. Quantum mechanics is nothing but quanta, or nothing but quantity. So this quantity is going to be quanta, this quanta is going to be quantum. So this is something related to quantity, quanta and quantum. And here Max Planck, and he is the person who tried to be the mastermind for this quantum mechanics. We also call this as Planck's quantum theory. We call it as Planck's quantum theory. So this quantum mechanics given by Max Planck, and he said that the energy is always proportional to frequency. And he said that energy is given by En equals to NhE. So this is the fundamental property of the Planck's quantum theory. So Planck's quantum theory says that energy is released in the form of packets, and these packets are called as quanta, consisting of photons of energy. And these photons of energy is given by En equals to n h nu, where n can be 0, 1, 2, 3 and so on, and h nu is the photon energy, where h is the Planck's constant, which is given by 6.6 into 10 power minus 34 joule seconds. And anyway, we know that S here nu represents the frequency which is measured in hertz. So this is the energy. So according to the theory, the energy is in the form of packets, and energy is discrete. So energy is in the form of and this discrete contains packets, and this packets is represented by this En equals to nh nu, or n equals 0, 1, 2, 3. H nu, h is Planck's constant, 6.6 in 10 power minus 34 joule seconds, and nu is the frequency. So here the energy is proportional to energy is a function of frequency. According to classical mechanics, energy was a function of wavelength, but here it is a function of frequency. So this is the Planck's quantum theories. So now this Planck's quantum theory, when it was established and when it was elaborated, finally we are going to get an equation which is given by E equals to 8 pi hc cube by this is the original Planck's law. The energy distribution. This is the energy packet and this is the energy distribution. According to this energy distribution, this E is a function of frequency now. According to classical theory, the energy was a function of wavelength, but according to quantum theory, the energy is a function of frequency. And this revolutionized the whole thing. And according to this, the ultraviolet catastrophe was comfortably, beautifully explained. And it explained that as the energy was getting increased, the intensity was also getting increased, but the intensity was moving towards the left side because of the frequency. There is a decrease in the frequency with increase in the intensity, and this is very comfortably demonstrated by these equations. So this is what the quantum theory is. This is the fundamental property of quantum theory. And this quantum theory opened doors, we call it as modern physics. So there are two kinds of physics, classical physics and modern physics. Anything which is dependent on, which is a function of quantum, we just call it as modern physics. Anything which is a function of free of to the quantum, we call it as classical physics. So now we have modern physics. So the first one is given by En equals to n h nu. This is the energy. So this is the energy what we were trying to do, or what we were trying to demonstrate. Now here we have one thing called as duality. So we are going to get into a concept of duality. So what is duality? Dual in the sense two. So here we are going to use these two things in the quantum theory. According to classical theory, what was it? The whole universe is made up of matter and energy. And this matter, if exists, energy and matter, both of them are the products of this universe. If you want to define, then matter and energy are consisting the universe. So here what is the case? The case is very simple. It says that matter is different, energy is different. So energy is manipulated to produce matter, matter is manipulated to produce energy. So we have matter and energy. But this duality concept has opened the doors. Because this duality has combined this matter and energy into matter energy. So now we just have one thing called as matter energy, or in short we call this as matter waves. So now we have only one thing. What is that called as? Matter waves. According to classical mechanics, it was matter and or matter or. So it can be matter and energy or matter or energy according to classical. But now quantum says it is not matter and energy, matter or energy. The whole universe is made up of only one thing, and what is it called as? Matter waves. And this matter waves is the product of duality. And here we need to come to know the duality. We call it as hypothetical statement, which is given by Mr. De Broglie. So let us study what exactly is the De Broglie statement is. So let us take this De Broglie hypothesis. Now hypothesis in the sense a theory which is just vaguely given out without any experimental proof. So here de Broglie has given lambda equals to h by mv. We call this as wavelength according to classical mechanics. But here it is not a wavelength of wave, it is a wavelength of matter wave. So here lambda you call it as the wavelength of matter wave. And here what does it say? So wavelength of matter wave lambda is given by h by mv, where mv is the momentum possessed by the particle or matter. So lambda is the property of a wave and momentum is the property of a matter. So here both of them are interrelated to each other. How exactly are they related? Let us see in this way. How? Let us take the momentum. Let us take the angular momentum. How are we going to define the angular momentum? The angular momentum is given by, the angular momentum is always given by m into v into r. This is the angular momentum. And whose angular momentum is this? The particles. And what is the property of this particle? Of mass m. So when a particle of mass m is moving in a circle of radius r, a particle of mass m is moving in a circle of radius r with a velocity v, then the momentum possessed by this is given by angular momentum, which is given by m into v into r. This is according to classical mechanics. But what has de Broglie done? He didn't do anything except he just equated this whole thing to h, the Planck's constant. And here r is nothing but the radius, and this radius is converted into what? The wavelength. So r is replaced by wavelength, and what are we able to get? mv into lambda equals to h, or lambda equals to h by mv. So here we got lambda equals to h by mv, where lambda is the wavelength, h is the Planck's constant, m is the mass, and v is the velocity. So now we have two beautifully demonstrated hypothetical statement given from the classical of angular momentum. Instead of the radius r is represented by wavelength, and therefore presumably lambda equals to h by mv. So therefore the wavelength lambda is given by h by mv, and lambda we call it as de Broglie wavelength. So it is not a normal wavelength, it's a de Broglie wavelength. And what is this de Broglie wavelength? This de Broglie wavelength is going to correspond to the wavelength of the matter wave. So now let us calculate the energy now, because now we got a wavelength, we need to calculate the energy. So let us calculate the energy of this. Let us calculate the energy. So these are the fundamental principles of the quantum mechanics. So quantum mechanics says that energy is not continuous, it is discrete, and this is in the form of packets, and each packet consists of n h nu, where h nu is the energy or photon, and is the number of packets. So now we know that energy. Basic energy is made up of what? Kinetic energy plus potential energy. And kinetic energy is always given by half mv square, and potential energy is given by mgh. We know this. And this is for a macro world. This is for a macro world. But when we have a particle which is moving with certain velocity, and when it is under some voltage, when it is under some potential, then this is represented by kinetic energy represents the same half mv square, and this potential is given by the capital V. So here what is it going to get now? E equals to half mv square plus V. Or from this equation what will we have to write down? Half mv square equals to E minus V. Or from this, how do we write this? mv square equals to 2 into E minus V. Or multiply V on both sides, the velocity term on both sides. So what is it we have to get? Sorry, multiply M on both sides. When you want to multiply m on both sides, what will we have to get now? M square, V square equals to 2m into E minus V, or mv whole square equals to 2m into E minus V, or m into V equals to square root of 2m into E minus V. But what is this mv? mv is the momentum of a particle, which is exactly given by lambda equals to h by mv. So we are going to substitute this value in this equation. So finally what are we going to get now? Lambda equals to h by square root of 2m into E minus V. So this is the wavelength. And this is the wavelength of whose? The matter wave. So we have a particle of mass m. When this particle of mass m is subjected to the potential V, then it is going to have a wavelength. And that wavelength is exactly given by lambda equals to h by square root of 2me minus v. So this is the de Broglie wavelength, and this is the de Broglie wavelength represented in the velocity, and this is the de Broglie wavelength represented in the energy and potential. So this is how exactly the quantum mechanics is moving. So now, how are we going to define once again? Let us start this quantum mechanics. The quantum mechanics is built on the failure of classical mechanics. And what are the failures of classical mechanics? The classical mechanics could not explain the ultraviolet catastrophe. It could not explain the continuity of energy or discreteness of energy, and it could not explain the energy relation with respect to frequency, because classical thinks that energy is always a function of wavelength. But quantum comes and Planck comes and he changes this whole picture, and he says that the energy is not continuous, it is discrete. And discrete, which is written in the form of packets, and taking this into packet, de Broglie has given a hypothetical statement where he said that the whole universe is only made up of one thing, matter, wave, and that matter wave is represented by lambda equals h by mv, where lambda is the wavelength, h is the Planck's constant, mv the momentum of the particle. So here, what is the case? The case is very simple. When a matter wave is going to have a wavelength properties, its particle properties will be less. Or when the particle properties are more, its wave properties are less. Which implies that even I can behave like a wave, or wave can also behave like a particle. This is what the concept of this de Broglie wavelength is. So wavelength can behave like a matter, or matter like you and me can also behave like a wave. Even we can become, or we can behave, or we can also be a wave. Is that clear? So this is what the fundamentals of quantum principles. So let us discuss another concept called as Heisenberg's uncertainty principle. Let us discuss one common term. What is called as Heisenberg's uncertainty principle. So let us see what is this Heisenberg's uncertainty principle. So Heisenberg uncertainty principle, which is represented by delta x dot delta p is given equals to h bar. So now what is delta x? The position coordinate. Delta p, the momentum, which is greater than or equal to h bar. So this is the Heisenberg's uncertainty principle. Before going there, let us have a basic description. According to classical mechanics, there is a body of mass m which is falling freely from height h exposed to acceleration due to gravity. So therefore, taking